Hello again. Right, so we're here the next week. Glad you're still with us. And we're moving on to a new topic of vectors, which should support some of the applied work you're going to do very soon. And here's Buster. He's helping today, not Squirrel. And we're doing vectors. So we've got to understand what a vector is. You'll have met these before though. We've got to be able to add and subtract vectors and multiply them by a scalar. We've got to know when two vectors are parallel. We've got to know the unit vectors of I, j, k, to know what a position vector is, to be able to find the distance between 2 points, and be able to find the midpoint of a vector. Right. Okay. A vector. Oh, by the way, hopefully you have to print out the PowerPoint sheet if you want to use it, so you can just fill this in. I've sent you it with the homework email, so all you have to do is print on PowerPoint 4 slides to a sheet on landscape, and it'll come out pretty nice. So anyway, it'll be just big enough for you to fill in. Right, so hopefully you've printed it out. If you want to pause and print that out, great. But if you're making your own notes, that's also okay. I have plenty of paper. You might have to pause the video to keep writing things down as we go along when necessary. Anyway, representing vectors. A vector is a quantity that has both size and direction. Another word for size we've got here, we can fill this in, is magnitude. So let's put it in there. Displacement, velocity, acceleration, and force can all be vectors. They can be described fully by their magnitude and direction. Thus, before starting our work on mechanics, we're going to look at vector properties. We can write the vector as A to B. That's that vector there, go travelling from A all the way to B. Or by using a single letter in bold, which is that bold A there. Or if we haven't got bold pens, we just write A with a little squiggle underneath or a straight line underneath is fine. We can represent this movement using a, do we know? A column vector. Oops. What's called a column vector. And in this instance, those pictures aren't quite right. Straps aren't right. But it's basically 6 along and 3 up. The orange bit's a bit wrong. So we write 6 along, and that represents the 3 up. We can also do it in 3D. Here we've got 5 along. Well, it depends on how you look at it, doesn't it? -3 in one direction and -2 in the other. And if you've got 3 directions, then the third direction is called the Z direction. Adding 2 vectors is equivalent to adding one vector followed by another. Let's see. Suppose we've got these 2 vectors. Find A plus B. So the diagram represents what's going on. Vector A is saying go along 5 and up 3. Vector B is saying go along 3 and down 2. Well, the vector A to B is going from A all the way to B. And by magic, I don't mind that magic, You can count these squares if you want. That is 8 along and 1 up. And you can get that also by adding the numbers. 5 plus 3 is 8, and 3 plus minus 2 is 1. Super. We can think of subtraction of two vectors, A take B, as A add the negative of B. This means B going in the other direction. So, for example, here we have these two. Here's our vector A, there's our vector B. Now, our vector minus B is the same as B if you look at it, but it's going in the opposite direction. So, A take B would look like that. And you can see from counting the squares there, 1, 2, 3, 4, 5, 6, Buster's restless, and it's gone up 1. We can also get that 6, 1 from doing A subtract B. So 4 take minus 2 is 6. 4 take 3 is 1. So two vectors, just to note, are equal if they have the same magnitude and direction. So it doesn't matter that we've got vector A here and vector A there. They are doing exactly the same thing. If I was to move that across, it would just go over the same thing, and that is minus B, and that's minus B. So it doesn't matter if you draw them elsewhere, as long as they're doing 4 along, 4 up, it's still going to be a vector A. Multiplying vectors by scalars. Remember, a scalar quantity can be represented by a single number. It has size but no direction. A vector can be multiplied by a scalar. For example, suppose a vector A is represented as follows. The vector 2A has the same direction but is twice as long. So vector A was that, then 2A, which I've tried to squeeze on there, I have to draw it above myself, 2A, we just multiply them by 2, 6, 4, it's easy as that. So we can actually say that these two vectors are, what can we notice? They are parallel, because they're a multiple of each other. The vector's a multiple of another one, then it's just parallel. In 3 dimensions, what we call the unit space vectors are I, J and K. That should all be bold, should those, that run parallel to X, Y and Z axes. They have a magnitude or a length of 1. So a length of 1 in each of the directions. So the I vector is 1, 0, 1. The J vector is 0, 1, 0. And the K vector is 0, 0, 1. For example, 3-dimensional vector can be written in IJK. Well, there's our IJK. The IJK as minus I, that should be bold, we can't do so, underline, plus 6J minus 3K. And if you see a vector written in that form, it's actually called, if I get this right, component form. That's called component form. So vector arithmetics, arithmetic vectors, or whatever you call that. Given that A is this and B is that, find 3A, take 2B. Well, 3 lots of A, I like column vectors, so I'm going to change them into column vectors. So 3 lots of A, which would be 2 minus 4, 1. Take away 2 lots of B. No I's, 1J and 2K's, so like that. If you work this out, that would be 6 take 0, which is 6. Minus 12 take 2, minus 14. and 3 take 4 minus 1. So we have that. If you had to write it back in component form, that would be 6, same as 6i, take 14j, take k. Second question, which of these is parallel to a minus 2b? Not going to work anything now, we just look for a multiple. So what's a multiple of 1 take 2b? First one isn't, it's not a take, is it? Second one, what do we think about that one? We can see if you divide by 4, you get 1 take 2b. How about the next one? Could that be true? Yeah, because if you multiply that by 2, you get 1 take 2b. So that's one as well. And that one? No. So they have to be multiples of each other. So we're looking for multiples. Multiples of a minus 2b in order to have made those decisions. Right, the midpoint of a line, segments connecting points with positions vectors a and b, has position vector half of a plus b. So the midpoint's just half of a plus b. Find the midpoint for these two vectors here. So all we have to do is work out what's half of a plus b. So we'll do the plus in now. 4 plus minus 2, 2. 3 plus 7 plus 3, 10. And then that equals 1, 5. So that would be the midpoint of that line joining those. Okay. Right, position vectors, interesting. Position vectors, so I'll write that again. Is a vector that is fixed relative to a fixed origin. For example, the position vector of P is given by O to P, comes from the origin, or just a bold P. And in this case, if we read it off, it is, I think if you count the squares, works out 4, 6, 4 along, 6 up. Is that right? Yes, it is. Oh, it's come up. Oh dear. To rub that out. Q is position. So what's that one going along? 1, 2, 3, 3, 2 down. So we're going to call that one. That doesn't happen. I have to rub it out. 3 minus 2. This in mechanics may be referred to as the, if you know this one, I think before I write it, the displacement vector of O to Q. It did come up, didn't it? Okay, midpoint of a line. Let M be the midpoint of P to Q. There he is. Yes, you can read him off straight away by counting squares, but I don't want us to do that. What is the position vector of O to M? So without counting squares, getting O to M, we can do this if you think about what's going on here, without using that formula that we had. could use a formula, where you go to get from O, where we know, to get to M, we would go from O maybe to P, and then go halfway along the vector P to Q. On the way to think of it, so O to M, what we do, we go from, if we put it in vector form first, and this is where we're done, we go O to P plus a half P to Q. Now we know that O to P is just the vector P plus a half of, now P to Q, to get from P to Q, you go back on the P along the Q. So that is, in fact, back on the P, so that's minus P, and then along the Q. So P to Q, travel along the blues, minus P plus Q. And we only want half of that, so halfway along the line. So then just sorting out the letters there, P plus minus half P gives us then a half of P plus a half of Q, which is what we said the formula was before, but that's a bit of proof of it there. If we just want to work that out in terms of numbers that we've got here, just to see how it all works. So that's a half of P. I think we said P was on the previous slide 4, 6. And a half of Q, which we said on the previous slide was 3 minus 2. So a half of 4 plus a half of 3. That's a bit of a fraction, isn't it? Works out, if you're going to use your calculator, as 3.5, I think, for a fraction equivalent. And a half of 3 plus a half of that gives us, sorry, a half of 6 is 3, and then it's take 1, isn't it? So that gives us 2. And that's our answer. On your whiteboard then, let M be 2/3 along the line of Q to P. So it's 2/3 along that bit, so 1/3 along the other bit if you want to use that fact. Work out what O to P is first, please, in numbers, and then try and find what O to M is. So pause the video, have a go, and we'll pop the answers up. Now hopefully you've had a go. You've paused it, you're ready to unpause. Here are the answers. 7/3 and 5/3. Hope you got that. Right, it says do match cards. We normally do some match cards here in pairs and things, but we can't really do groups. Still think the match cards are quite relevant, so I'm going to let you see if you can match them on the screen. But before that, here's a bit of intro to them. It gives you these facts. Tells us about vector A, B, C and D, but gives them in these funny forms. It hasn't really called them column vectors here. This is in fact the same as O to A. And this is O to B. This is meant to write that as O to C, and that's O to D. You can write them all as column vectors. That's obviously as a column vector, so is that. This may be not. You can O to C, or you can only call it C, remember, you just got it C. And it's 1, 2, 0. And this one, if you like it as a column vector, is 1, 0, 2. And you're asked in these puzzles things to match things up. You might be asked, what is vector A? Well, vector A is the same as O to A. And that's, oh, it's just writing that one down, isn't it? O to A, 1 minus 2, 3. Vector B is O to B. And that'd be minus 2 minus 3, 2. A bit easy. Vector A to B, remember if you're drawing it with the position vectors, so that must always come from 0. Vector A, remember, is coming from 0 up to A. Vector B is the vector, that's A if you want to bold A, or O to A. And this could be vector B, which is O to B. So actually travelling from A to B, you want to going here to there. So it's that's the vector we're really after. You have to go back on the A and along the B, don't we? So that is in fact, write it the right way, other way around, is B take A. And if you work that out, B take A, challenge form here, minus 1 take 1, minus 3 take negative 2, so that's add 2, and 2 take 3 is minus 1. Hope I've got that right. Or you might see it written as minus 2, 1, 1. Just another way of writing it. Or it could be written as minus 2i plus minus 2j. Oh, it's minus 1j. Oops, sorry. Minus just k. Yeah. That's probably rub it out. And this one, B to A, is going in the opposite direction. So you actually want to go the other way. So that actually works out as A take B. Line all those. If I keep that one as columns going the other way, you can see that B, A take B. So 1 take minus 1 is 2. That take that. So that's 1. And 3 take 2, 1. So it's in fact the same as that vector, but with a negative. That had a negative, and this has positive in front of it. Maybe you knew that. Right, so the matching up is here. It's the same vectors A, B, and C. A reminder of them's down there, or you may need to rewind the video and just jot down what A, B, and C were. Vector form. You're meant to match all these up. So in other words, you work out A to C, and you match it up with a box which has got a red box around it. So every one single box matches up with a double box. So have a go. You should be able to match and match each one together. If you jot them down, and then you should get them all paired up. Everybody has a pair. And I think, yeah, straightforward. The only one that's a little odd is you have to match that one with something, and that with another letter one. But that should be able to think that through. Hope you managed to get them all in pairs. If you do, you know you've got it right. Unless you just put them in random pairs. But I'm sure you'll be able to think this one through. Fairly simple. When you've done that, there are some other questions to do related to this. Again, I say you never have to do all the questions here. Just do what you feel comfortable with. If you're finding them easy, just do 1 or 2 from each, or just do 1 from each question. If you're finding it tricky, you may have to spend a bit more time on it. 3 questions there. You pause them back and have a look, or try and remember to put the worksheet on your thing. Maybe just pause them and have a look. It's easy enough, isn't it? And 4 to 6 questions there. So if you find these easy, just jump to the harder ones. Okay, and finally, the answers to all those 1 to 6 questions. All parts are there. Say, please don't think you have to do them all. Just do what you feel you're comfortable with. If you're clueless, maybe you will have to do them all, but if you feel it's easy, then just pick and choose some questions from those. Right. think that's about it from me for this lesson. See you next time. Vectors 2's coming up. I bet you can't wait.